So, good evening to everyone present here. So, I welcome you all for the day 2 online FDP program on advanced polymer composites for aerospace and mechanical applications. So, for today's session, it gives me immense pleasure to introduce today distinguished speaker Dr. Gurusideswar, working as assistant professor in the Department of Aerospace Engineering at SRM Institute of Science and Technology, Chennai. Dr. Gurusideswar holds a PhD in Aerospace Engineering from IIT Madras, along with ME in CAD Computer Design and a BE in Aeronautical Engineering from Anna University. With over 9 years of academic and research experience, he is an expert in the field of composite material and structural mechanics. His research interests span across natural fiber reinforced composites, AI-driven material optimization, smart material integration, fracture mechanics, and machine learning applications in structural health monitoring. He has over 30 publications in reputed journals, published a book and a patent grant on high strain rate tensile testing setup using impact loading. Dr. Gurusideswar is a recipient of numerous accolades, including the CET-KTR Research Award, IITM Alumni Travel Grant, and several certificates of appreciation for his teaching and expert lectures. He also serves as an innovation ambassador under the Ministry of Education Innovation Cell. We are honored to have him with us today, and we look forward to gain valuable insights from his expertise. Sir, please take it.
Thank you, Dr. Dinesh Babu. Thank you. Am I audible?
Yes, sir. Yes, sir. Audible, sir. The screen also visible, sir.
Fine.
Yes, sir.
Just a minute.
Yes, sir.
Yeah. Very good evening to one and all. So, I am going to give a talk on dynamic response of advanced polymer nanocomposites for aerospace applications. So, basically, I am going to cover external insights from drop mass setup to Hopkinson pressure bar and a few microstructural calculation studies. So, this is what I have planned for today's talk. Once again, welcome all of you. So, let me start my presentation. So, this is my roadmap of my presentation. So, I would like to give a small intro about nanocomposites and how to prepare nanocomposite specimens, and also how to characterize the dispersion of nanofillers in the polymer. So I'm going to address few microstructural characterization techniques in this talk, and then I'm going to cover few mechanical characterization, starting from tensile, structural impact to few mechanical testing studies. And then I will come to the main agenda of today's talk, the high strain rate characterization of composites using drop mass setup. And also I'm going to cover digital image collage technique. So it is one experimental tool to understand the strain contour of composite samples. I'm going to brief about the digital image collage technique. And finally, I will cover high strain characterization of composites using Hopkinson pressure bar or Kalski bar. So this work I am going to present from my postdoctoral work. And finally, I will summarize the whole presentation. So this is the roadmap of today's presentation. So you all know what is nano. So the particles having one or more dimensions of 100 nanometer or less than 100 nanometer, and physical and chemical properties should also be differ measurably than those of the material is called nanoparticles. So I hope you all from mechanical background, I believe that you know what is nanoparticle. So there are so many nanoparticles are available. People are doing research in these nanoparticles. Example, nano clay, nano alumina, carbon nanotubes. So there are so many nanoparticles. Now, what is nanocomposites? So the nanocomposites is nothing but in order to improve the performance of the composites, if any one of the dimension of the particle is dispersed in nanometer range, then it's called nanocomposites. For example, I can add nano clay with epoxy, then it is called as nanocomposites. Similarly, I can add carbon nanotube with the epoxy or polyester, then I can call it as nanocomposite. So again, how can we differentiate nano fillers? So based on the geometry, we can have so many types. So one is in the nano fillers come in layers. So for example, if you see this figure, you can see my laser pointer. So it has the nano size thickness and micrometer dimensions. So it is called layered layered nano fillers or nano layers, we can say. So example, nano clay. So if you, and again based on geometry, if you see nano tubes, the diameter of that tube is in nano level, wherein the length of the tube is in micrometer level. So again, it is nano, we can show nano filler. And third thing, we have so many 3D nanoparticles starting from spherical, cylindrical, cube. There are so many nanoparticles are available in the market. So based on the geometry, we can have nano layers, nanotubes, or 3D nanoparticles. So this is a quick intro about different types of nano fillers based on the geometry. So again, as I mentioned earlier, what is nanocomposites? It is a two-phase material where one of the phase is dispersed in the second one on a nanometer scale. So this is called nanocomposites. So in today's presentation, I am going to use my epoxy as a matrix and a nano clay as a nano filler. So it is called nanocomposites. It's a two-phase material. So again, I have given a quick summary about the nano clay. It is also called as layered silicate. As I mentioned earlier, it looks like a thin layer. So where the thickness of the layer is in nanometer and the length and breadth of the layer is in micrometer. So it is, so if you see, it has 1 nanometer thickness approximately, and the lateral dimensions may vary from 30 nanometers to several microns. So because of this, the thickness and the lateral dimension, we can get high aspect ratio. So that is why we can achieve very good mechanical properties with the addition of nano fillers in the epoxy. So again, the adjacent layers are separated by a regular van der Waals gap. It is called interlayer. We are going to see in detail in the upcoming slides. So basically, if you see, to get an idea of a nano clay, so here this is the scanning ultra micrograph of a raw clay. If you see, it looks like a thin layer where the thickness of the layer is in nanometer and the lateral dimensions are in micrometer. So it is in aggregated state. That's why it is clumped. So this is the typical micrograph of a nano clay. Now types of nano clay. Again, there are so many types. Based on that, I don't want to go in detail. But in this study, we are going to use Mont-Molinite clay. So it is one type of clay which is commercially available. So in this study, I am going to talk about this MMT clay. So why MMT? Again, there are so many reasons from the literature. It has high aspect ratio. It has unique intercalation and exploration characteristics. And it has high specific surface area. It is environment friendly. And it is easily available in large quantities at low cost. So because of this, this Mont-Molinite clay is popular in composite research. So there are so many commercially available clay in the market. So just I have summarized the commercial name of the clays, starting from closite. It has several types under closites, and bentone, nanomer, nanofill, delite. Like that, there are so many commercially available clay are available in the market. In this study, we have used Garamite 1958. This is a commercial name from Southern Clay Products USA. So this Garamite is nothing but it is a modified Mont-Molinite clay. So we have not used a raw clay. We have modified the clay. That is called Garamite. This is a commercial name. So this is the clay we have used in this study. Now coming to the dispersion structure. So now I have a clay like this, I have already mentioned it is in layer form. So you can see. So now I can take a pinch of nano clay. I am going to mix with the polymer. The polymer could be any polymer, could be a thermoplastic or thermoset. Here we have used thermoset, that is epoxy polymer. So when I mix the nano clay with the epoxy matrix, how what would be the outcome? So here I have shown. So we can expect three different kind of dispersion types. One is phase separated disc microcomposite, again intercalated, again the clay is mixed in agglomerated stage, and this is exfoliated. So here if you see, the nano clay is dispersed well in the epoxy. So this is the good dispersion we can say. But here it is good, but again if you see, all the clay has been arranged in a parallel fashion. So this is not good. So this is the three kind of thing we can achieve once we mix here the nano filler with the polymer. So let us see one by one in the upcoming slides. So history, again, this nano clay was discovered by Toyota Group from Japan. So these guys are the first guys who tried nano clay with polyimide matrix, and they found good improvement in the mechanical properties by adding of nano clay with polyamide, and later it was extended to other polymers, to epoxy, polyester, and so on. So now how to prepare the composite sample? So we need a matrix, so we need a polymer. So as we are doing this study for aerospace application, so we have chosen a DGPA resin, that is digyl ether bisphenol A resin, which is aerospace grade resin, and we used triethyl tetraamine as a curing agent, and also we used typical E-glass fiber in order to understand the effect of clay in composites. And again, as I mentioned earlier, we used modified Mont moldonite clay. The commercial name is Garamite. So these are the materials which we have used in this study. Now I have a epoxy, I have matrix, I have a nano filler. So by mixing the nano filler with epoxy, I will get nanocomposites. Now, as I mentioned earlier, we cannot blindly mix the clay with epoxy. So we need to take some different clay content. So based on literature survey, we have chosen 1.5 weight percentage, 3 weight percentage, and 5 weight percentage as the nano clay. That means, for example, if I take 100 gram of resin, I can take 1.5 gram of nano clay and then I can mix. So this is called 1.58% epoxy clay nanocomposite. Similarly, I can have 3 weight percentage nano clay epoxy nanocomposite and 5 weight%. You may ask a question: why I have chosen 1.53 and 5? Why I have not gone beyond 5? The reason is, as I mentioned earlier, it is nano fillers. So if I increase that the clay content, then we may not mix the clay well with the epoxy. So that is why we stopped with 5 percentage. So just we have chosen 3 different weight percentage in order to understand which content would be the optimal content for getting better mechanical properties. And how to disperse it? So now I have taken a different clay percentage and I have taken epoxy. So we use a typical mechanical stirrer for mixing the clay with epoxy. Again, to have a better dispersion, we use ultrasonicator. So this is the procedure to prepare the epoxy clay nanocomposites. So now I will cover this 4 topics. Microstructural characterization. So I wanted to emphasize, why should we go for microstructural characterization? The reason is, as I mentioned earlier, we are dispersing, we are mixing a nano level clay in epoxy. So we need to understand how it is dispersed in the epoxy. As I mentioned earlier, it is a nano size. We cannot see naked eye. So we need to go for some microstructural characterization. By using these techniques, it is possible for us to understand the quality of dispersion of clay in epoxy. That's it. So from that we will understand whether the clay is mixed well in the matrix or not. For that reason, we have used these 4 different techniques. I will be going one by one. The first one is X-ray diffraction. It's very common in polymer characterization. So we used a wide angle X-ray scattering. So if you see here, the black one shows the raw clay. That means simply we took a pinch of clay and we have done the XRD. So you could see a lot of peaks. And then we took heat epoxy, there is no peak. Again, we took 1.58%, there is no peak. Again, for 3 and 5, we could see a peak. You can see here, the D0.1 peak at 2 theta 6.9 degree. So this peak indicates that sample has integrated structure. So I will tell what is meant by integrated structure. So if you see my laser pointer, so this left hand side is the integrated structure. So because of higher clay content, the clay is not mixed well with the epoxy. If you see, it is arranged in some parallel fashion. It is in agglomerated state. You can see. So that means higher the clay content, you get this kind of agglomeration. Wherein, if you see, this is exponent structure. Again, for 1.5 there is no peak, which indicates that it is the clay is mixed well with the epoxy. That means the distance between 2 layers is more than 7.75 nanometer. So that is the meaning. So that it is dispersed well. So from the XRD, we were able to confirm that 1.58% clay is dispersed well with the epoxy. So again, this is again a typical scanning ultra micrography of raw clay at different magnification. So it is at low magnification around 23,000 x, wherein here it is 60,000 x. So it is not dispersed with epoxy, it is just a raw clay. I just wanted to show how does a clay look like. So if you see carefully, it is look like a layer. It has a nano size thickness and micron size lateral dimension. So it is basically typically it is a layer. It's like a paper. So this is what we could see from the micrography. So we also have gone to small angle X-ray scattering. So the idea is, if you see my previous slide, my first peak was observed at 6.9. So, but we could not go below 5 degree. So for that purpose, for that reason, we have gone for small angle X-ray scattering. So if you see, we can go to small angles. So here also you could see that black is clay, that red is 1.5, where 1.5 doesn't have any peak, which means the clay is dispersed well with epoxy. The 3 and 5 has a peak at around 5 degree, which means it has the dispersion is not good, it is integrated. So this is a TEM, again this is the micrograph from transmission electron microscopy. So if you see for 1.5 by 8%, you could see it is dispersed nicely, wherein the higher clay loading, you can see it is agglomerated. So this is what we could see from the XRD and transmission electron microscopy, TEM. So and also from the scanning electron microscopy, we wanted to understand that the composition of nano clay epoxy composite. So it has basically it has magnesium, aluminum, silica. We also tried this laser induced breakdown spectroscopy for our research work. Again, this study was used in Chandrayaan mission also. So I had the opportunity to do this testing under the guidance of Professor Nilesh from IIT Madras. So from that laser induced breakdown spectroscopy also, we could see the epoxy has hydrocarbons, wherein the epoxy clay has magnesium, magnesium, silicon, aluminum. So these are the alumina. So these are the main composition of the clay. So which we have confirmed from the EDS and LIPS, energy dispersive spectroscopy, and less induced breakdown spectroscopy. So just we have confirmed the composition of epoxy and clay. So this is a small study. We wanted to understand the effect of clay. So just we were curious to understand to know the energy required for the laser plume. So we have done it for two different samples. One is for epoxy clay, other one is for glass epoxy clay. The left hand side, if you see, so for epoxy and glass epoxy, it requires less energy to make the laser plume, wherein if I add the clay, then it needs more energy. It needs more energy to get the laser plume. This is what we could see from this graph. So now we have done with the microstructural characterization. So from the XRD, that is X-ray diffraction, and from the transmission electron microscopy, and from scanning electron microscopy, we have understood the dispersion of clay in epoxy, and we have noted that 1.58% clay has given good dispersion, wherein 3 and 58% have given integrated structure. So this is what we have found from the microstructural studies. So now the samples have been prepared. The dispersion of clay in the epoxy have been understood. Now we need to go for the next level, macro level testing. So now the main aim of adding the nanofiller with epoxy is to improve the properties. So that is why we have done all that sample. That's why we have prepared the sample. So now we are going to see in a nutshell the effect of mechanical properties, thermal properties, and electrical properties with the addition of clay in epoxy. So let us go one by one. So I have not gone in detail. I am not going to go in detail. So just I want to give a glimpse. So with the addition of clay, what kind of improvement you will get? So this is what I wanted to focus. So by addition of clay in epoxy, we could see a good improvement in the tensile modulus, the tensile strength, and also flexural modulus, flexural strength, and also impact strength. So all the green color values are shown the improvement in the percentage with respect to the neat epoxy. So this is the typical fracture surface of epoxy. Again, this is the fractography which was taken after that from the failed sample. So now we have also carried out a similar testing for composites. If you see, this left hand side shows the effect of clay in polymer. We also wanted to understand the effect of clay in a typical composite. So what is composite? A composite should have a reinforcement called fiber, and it should have a matrix called polymer. So we used a glass fiber reinforced polymer for this study. So also we have tried different clay composition. So again, if you see in the right hand side, we have got some minimal improvement of the mechanical properties with the addition of clay in the glass epoxy composite. So you may ask a question. If you see the number, in epoxy the improvement is high, wherein in glass epoxy the improvement is bit lower. So the reason is, you all know the tensile, the fiber is the major, the dominating mode of failure. The fiber will take the major amount of load. So wherein the matrix is not is a secondary. So that is why in the tensile test of glass epoxy clay nanocomposite, as the fiber is dominating, the fiber is the main element to take the load. But even though the fiber is the dominating element, but still the addition of clay in a matrix all lead to a minimal improvement in the properties. So this is what I wanted to convey. The effect of clay in polymer matrix and the effect of clay in a typical glass epoxy composite. So if you see that the bottom figure, again this is a scanning electron microscopy of a failed sample. So because of the addition of clay, one can see a strong bonding of matrix with fiber. You could see. So this is what we have found. So because of this strong bonding, we could get better the proper mechanical properties due to the addition of clay in the glass epoxy composite. So again, thermal stability, it's a very simple test characterization to understand the decomposition temperature of that epoxy. So we used thermogravimetric analysis for this study. So if you see the green color, so this is the left hand side shows the mass percentage. The x-axis shows the temperature. So when I keep on heating the sample around at 300, there is a drop in the in that curve. So that means it shows the weight loss, mass loss. So this can be confirmed from the derivative curve of this curve. You can see this. You can see a peak. So this peak indicates the first decomposition temperature. So this is here we could see a 10 to 15% of weight loss. So again, if you see the second decomposition starts at around at 560, you can see from the graph. Again, at this second decomposition, there was a weight loss of 50 to 60 to 70% of weight loss. So what is the outcome? So with the addition of clay in epoxy, we could see a shift in the decomposition temperature. So because of course clay is a ceramic material, it has silicon alumina, of course. So because of this ceramic composition, we got a better thermal stability. So this is what we have found from the thermal properties. Then coming to that electrical properties. So already we have seen the effect of clay on mechanical properties, effect of clay on thermal properties. Now finally come to the electrical properties. So if you see, so the idea is we have made different samples, epoxy sample and the clay epoxy clay samples. So we applied a high voltage to these samples, and we see its breakdown voltage. If you see that the photograph of that neat epoxy without clay, that there is a major damage, wherein the right hand side 1.58% clay epoxy, you can see minimal damage. So because of clay, the breakdown voltage is increased with the addition of clay and epoxy. This is what we have found from the electrical properties of epoxy clay nanocomposites. So we have seen, quickly I'll give you a summary what I have discussed so far for the sake of better continuity. So initially I talked about what is nanofillers, and I have talked about what is nanocomposites and the history of nanocomposites, and then I have talked about how to prepare nanocomposites. I have talked about the raw materials, and then I have talked about the microstructural characterization of composites starting from XRD to SEM to TEM, and then we have seen the effect of clay on mechanical properties, the effect of clay on thermal properties, and finally we have seen the effect of clay on electrical properties. So now we have understood what is nanofiller, how to prepare a nanocomposite, and how to do the characterization of nanocomposites. And also we have noticed that the addition of nanofillers in the matrix leads to a significant improvement in the mechanical, thermal and electrical properties. So now I'm going to take you to some advanced characterization techniques, which is the main agenda of today's talk. So I'm going to spend some time on this. So I hope all of you are aware about strain rate. So here I have given a few summary about strain rate. In general, the composites are rate sensitive. For example, one second. For example, when I pull that sample slowly, I will get some kind of mechanical property, tensile property. Similarly, when I pull that sample at a high speed, rapidly, then the properties may differ. So this is called rate sensitive. So I will come to this point. Why do we need to understand the rate sensitivity of composites? Let us go one by one. One second. Yeah. So in general, composites exposed to high energy, high velocity impact loading. So we need to understand the dynamic behavior of the composites, and also we need to develop the dynamic failure criteria. So for that also, we need to know the mechanical properties at high strain rates. Yeah. So here I have shown how to carry out the studies using different experimental techniques. So one is conventional loading frame, which is available in institutes and in the basic UTM, universal testing machine. With that, you can achieve low strain rate. And if you have servo-hydraulic testing machine, you can achieve medium strain rate. And we can also use drop mass setup to achieve intermediate strain around from 100 to 1000 per second. And also to do high strain rate, very high strain rate studies, you can use the split Hopkinson pressure bar or Kalski bar, where you can achieve up to 10,000 strain rate per second. And if you want to do very high strain rate, ultra high strain rate, then we can go for expanding ring, that is above 10,000 per second. So in this study, I'm going to focus on drop mass setup. So this is the one nice technique which fills the gap between the conventional low speed and high speed instruments. So now here I have given the strain rate regime. As I mentioned earlier, the low strain rate is categorized from 10 to minus 6 to 10 to minus 3 per second. It's called quasi-static. So we use conventional cross-head devices. So from this, we determine the properties of samples, say tensile strength or tensile modulus, so and so. So this is called quasi-static testing. And for medium strain rate, it is intermediate. We use servo-hydraulic machines and drop mass. The example is plane crash. So this is the typical example. So when two planes get crashed at this junction, the material may experience this intermediate strain rate. So this is what I wanted to convey. So it is ranging from 10 power minus 3 to 10 power 2. Again, high strain rate. Again, 10 power 2, 10 power 6. Again, we use Hopkinson pressure bar. Again, the application is the bullet impact and blast applications. So during this application, this high strain rate will be experienced. Again, ultra high strain rate, we use stellar impact and plate impact, and application again nuclear explosion. In these areas, the material may experience ultra high strain rates. But in this study, I'm going to focus only on drop mass setup, and I'm going to focus on this Hopkinson pressure bar. So these two I'm going to focus. So let us see one by one. So before that, you should understand what is strain rate. It is nothing but it is the cage length. One second, maybe I can write here so that you will get better understanding. So cage length divided by the crosshead speed. So this is called strain rate. So that is the cage length is in millimeter. That speed is, we say, in millimeter per minute or per second. So when you divide, you get strain rate. So this is what I want to convey. So so with the help of drop mass setup, we can achieve from 10 to 1000 per second strain rate. It is inexpensive. It can accommodate different geometries. So we can get different variation of strain rate. So this is the typical drop mass setup which was developed at IIT Madras. You could see here. Now you may ask a question: how to achieve high strain rate by simply dropping the mass? So the idea is, again, from that. One second. Again, V is equal to root of 2gh. So from that energy principle, we know that the velocity is equal to root of 2gh. That means higher the height leads to higher the velocity. So from this only we can get different strain rate. One second. Yeah. So this is the picture which we designed to do that high strain testing. For example, if you see, you can just observe my laser pointer. When the drop mass hits that fixture at this point, so then the sample will fail in the tensile mode. So when the mass impact at this point, maybe I can show with that with the pen. So when the mass hits this place, then the sample will try to fail in a tensile mode. So this is the principle behind this. So this is what we have used. So just by dropping the mass, it is possible for us to apply the high strain rate loading to the composite sample. So this is what I wanted to convey. So now, so we have got, if you see this picture here, we have a load cell, the PCB load cell, piezoelectric load cell. From this, we get the load data. Again, to get the strain data, we have used a digital image correlation technique, that is non-contact strain measurement. I am going to show in the upcoming slide. From that, we got the strain data. So from this, we could plot the stress strain curve. So from the stress strain curve, it is possible for us to understand the effect of strain rate. So why DIC? So again, I hope you all are familiar with that the instruments. When you do a typical tensile testing, we use extensometer, right, to measure the strain. In some cases, we use strain gauge. So if you use extensometer, it gives strain between 2 points, correct? Similarly, if you use a strain gauge, it measures strain over a small area. But with the help of DIC, this digital image correlation, it is possible for us to get the strain over the whole area. So this is one advanced technique which we have used in this study to understand to get the strain data. So the application of DIC is very very large. It is used in fluid mechanics. It is used in fracture mechanics. It is used in many applications. Anyway, I am not going to this in detail. So this is the typical DIC setup. So we need to have a sample. In the sample, you need to have a spectral pattern, and you need to have light source, and you need to have a camera. So with this, you can get the strain data. So this is the typical DAC process. So first we need to prepare the sample and also we need to make spectral pattern and record the images of the sample before and during loading till failure, and finally post-processing. Once you get the images, do post-processing and get the strain data. So this is the three-step process which we employ in getting the strain data from the DIC, digital image correlation technique. So you may be wondering how to get this strain without having any physical instrument. So this is the principle behind. So this is the principle I have shown in this slide. So the DIC, this technique tracks the position of the same physical points shown in reference image and the deformed image. So basically, the DIC in the DIC technique, we focus that the gray level intensity. For example, the point A has dark black, which means it is very the gray level is very high, wherein B is gray. So by tracking this points, this gray level, it is possible for us to get the strain data. So this is before deformation, this is after deformation. That is why in order to track this, in order to understand this thing, we use that algorithm. We use some software to get this to track this points. So I think this figure shows a better insights. If you see you can see my laser. The top left corner is 249. If you see, because it is very bright, it has bright color. Maybe if you see this bottom, where you can see my cursor, it is 75 because it is dark color. So basically, in this we are tracking the different gray level from the sample. To get different gray level, we use this spectral pattern. We use this kind of spectral pattern. So from this spectral pattern, we can have a different gray level. From the different gray level, we can get the strain data. So this is the basic principle behind this technique. So just I have shown a typical photograph of a DAC setup. You can see a typical UTM. The sample is fixed. So we have kept a camera. So lights have been kept, and from the camera you can record the images. And then you can do the post processing, and then you can do the get the strain data. So there are so many parameters in the DAC technique. So one has to optimize the parameters. Again, I'm not going in this topic because of time. I want to focus on the results of that high strength studies. So this is the different spectral pattern. So we can get this pattern either by using a spray paint or by any other mode. So from the pattern only we can get that strain data. Now come to the main result of this study. If you see, so this is the typical stress strain curve of a epoxy clay nanocomposite. So if you see, this black shows the testing was done at low speed, that is at quasi-static. If you see, it is failed at around 50 megapascal. It has a strain of 1.6%. Now, if you do the same sample at high speed, you could see there is a drastic increase in the strength. It has gone from 50 to 80. Again, the strain has been reduced. Again, the stiffness is increased. So if you see, so this is what I was mentioning in that beginning. With the help of this DAC, we can get the full field strain data. So this is the sample of that epoxy clay. So you could see, just I am showing the different the strain contours at different time step. This is at 130 microsecond. When I keep on apply load, you can see there is a strain localization. Again at 330 microsecond, you could see some you can see a good amount of strain localization. Again at 530 microsecond, you can see there is a large, you can see a strain localization or strain concentration. So this is the point where the failure is about to happen. So this is the image taken just before the failure, and then we can have a failure. So what I want to convey from this slide, if you use any exosometer or any strain gauge, you may get only the numerical data. But when we use this digital image correlation technique, it is possible for us to get the qualitative data, and also you will get a more in-depth data from that given sample. So this is what I wanted to convey. So as I mentioned earlier, the epoxy clay is very sensitive to strain rate. At quadratic, it has different property, wherein when I do the testing at high speed, at high strain rate, say 385 per second, I have got different properties. So this is what I wanted to convey to this forum. Again, here I have shown the effect of strain rate on modulus, tensile modulus, for different samples. So the black shows the neat, and this red, green, and blue shows the clay samples. So if you see, when I keep on increasing that strain rate, my properties have been keep on increasing. So this is what we could see, and also we could see the addition of clay leads to improvement in the tensile modulus. For example, if you see, the black is the epoxy. We got 5 gigapascal as a tensile modulus, wherein this blue is the 5% clay. So with the addition of clay, we could get a improvement from 5 to 7 gigapascal. So this is what I wanted to convey to this forum. Similarly, this slide shows the effect of strain rate on strength. So this slide shows the modulus, and this slide shows the next slide shows the strength. You can see the strength. So again, strength we could not get good improvement in the 5% because, as I mentioned earlier, the 3 and 5 lead to agglomeration. Because of agglomeration, the sample lead to premature failure, and also some voids also were formed because of higher content of clay. So again, this is other figure, the effect of strain rate of a glass fiber enforced polymer clay. This slide shows the effect of strain rate of epoxy clay. There is only clay and matrix, but here we have fiber, matrix, and clay. So again, at quasi-static, the strength is around 250 gigapascal, 300 megapascal, wherein when I do the testing at high strain rate, it is increased to 450 megapascal. So from this, what we understand, when I do the testing at low speed, I get some properties. Similarly, when I do the testing at high speed, the properties will be different. So this is what I wanted to convey to this forum. So this is this is the figure just before the failure, and this is you can see the strain localization. So now coming to that micrograph, I think I'm running out of time. I'll come to that conclusion. So we also wanted to understand the effect of strain rate from the failed samples. So we have made the samples. The samples have been tested. Now we have the failed or the fracture samples. Now these fracture samples were taken to the scanning micrography. So from that we wanted to understand its behavior. So this is a micrograph of neat epoxy. One can see a smooth, glassy, and featureless fracture surface. This is a typical surface of a brittle material. Now this is the micrograph of epoxy clay. So you can see a rough fractographic features, deep river markings. Again, also you can see some clay agglomerations. So this is what we got from the epoxy clay composites. So again, this is the micrograph which we taken from the high standard samples. So if you see at quasi-static, the samples were very smooth. But when I do that, when we see that the photography at high strain rate, you can see a typical cleavage structure, and you can see very rough surface. So what I want to convey is the addition of clay shows secondary cracks and more deeper river markings. This is what we could see. Again, this is the micrograph of glass epoxy clay. So this is neat. You can see a fiber breakage, but for the clay samples, you can see a strong bonding of the epoxy clay with the fiber. So this is what we could see. Again, at high strain rate, we could see a fiber breakage and complete debonding of fiber from the matrix. So this is what the summary of this the phase 1. The drop mass setup was designed and fabricated for intermediate range of strain rates. It is compatible with digital image correlation to get strain data, and we observed that the tensile properties of epoxy and glass epoxy are very sensitive to strain rate. So this is the final the outcome from the study. So you give me another 5 minutes. I will cover this other part. I will take maximum 5 minutes. So this is the work which I have done for my postdoctoral work. So I will directly go to that the experimental technique. So far we discussed drop mass setup. So this is that setup called Hopkinson pressure bar or Kalski bar. So this is a one technique which we can do very high strain rate. So here I have given the schematic of that setup. So we use a gas gun. So from the gas gun, we can have a pressurized air. When the pressurized air is released, the striker bar will hit the incident bar. So when the moment it hits the incident bar, a stress wave will be generated. The stress wave will pass through the bar, and here we have the sample. So because of the impedance mismatch, some part of stress wave will be transmitted through the sample, some part will be reflected back. So here the main loading will happen. So these are the some the force history and from that study. Just I want to show that that microstructural studies of this sample. Yeah. So basically, we used ultra high performance concrete. Concrete was used in the study, and we wanted to understand the high strain rate behavior of this concrete. So you could see, again we used DIC, digital image correlation technique. You could see the different the photograph at different time steps. So at low speed impact, you could see a crack initiation, and then crack has grown. You can see a crack growth. Again, at high speed impact also, you could see there are more number of cracks formed, and it got propagated. You can see from that figure. So this is what I wanted to convey. So again, with the help of DIC, the digital image correlation, from the strain contour plot, we can see that crack initiation. See, you all know when the material is being loaded, the material will fail through crack growth, and then it will lead to final fracture. So we cannot understand that the fine crack using naked eye. But with the help of this DIC, you can see the crack initiation. At 90 microsecond, there is a crack is started generating. At 107 microsecond, you can see a big crack. Again, this is for one sample, this is for other sample. So you can see that how the crack has propagated with respect to loading. This is what I wanted to convey. So you can see here how the stack, at different time step I have given the crack growth. So you can see that this is the final failure of the sample. So again here, this is for other sample. You can see the crack is initiated, the crack is propagated, and finally it is led to failure. So this is what I wanted to convey. So these are some studies for compression testing. So again, you could see how the concrete is failed with respect to high-speed loading. This is what I wanted to convey. So you can see the arrow mark. This is the place where the crack is initiated, and then it has propagated, and then it lead to n number of cracks, and it lead to final failure of the sample. So just I wanted to convey, when the concrete is subjected to high standard loading, I just wanted to convey how the crack initiation lead to the final failure of the sample. So this is what I wanted to convey. I don't want to go in depth. So again, summary, as I mentioned, as similar to composites, concrete also is very sensitive to strain rate, and we were able to incorporate high-speed DIC technique to understand the failure pattern. So feature scope, I have given some features scope for this on this area. So there are a lot of scope to understand the mechanism and modify the nanostructure to achieve the required engineering properties. We can focus on test standards. Again, we don't have standards for high-speed testing, so there is a lot of scope on developing the standards for high standard studies, and also we can understand the mechanics of the steel fibers in concretes. So these are a few points which I want to focus. So these areas have a lot of scope for the future. So at this juncture, I would like to acknowledge my PhD supervisor, Professor Velmurugan, and other collaborators from engineering design, electrical engineering of IIT Madras. And also I would like to acknowledge my postdoc mentor, Professor Krishna Jalagada, and Professor Prakash Randagopan from again IIT Bombay for their support in doing these studies. Thank you all for your patient listening. I stop my presentation.
Thank you, sir, for an informative, interesting session on dynamic response of nanocomposites as well as the effect of strain rate on the composites, sir. So now we'll move on to the question and answer session. So if anyone has the question, please feel free to ask the expert or type in the chat box. Dear participants, if you have any questions, please feel free to ask or post in the chat box.
Hello.
Yes, sir, please.
Yes.
Yeah, sir. Very wonderful presentation. This is Dr. Manish Kumar.
Thank you.
And I'm faculty in Plastic Technology Department in HBTI Kanpur, sir.
Fine, sir. Fine.
Yeah. So, sir, I have one or two few questions because my background is also polymer nanocomposites. I did my PhD in that area. So, particularly, I want to ask that one thing, that the sample that whatever you have prepared for epoxy case, epoxy composite, nanocomposite, whether you have prepared the film or something else like ASTM standard sample for tensile or flexural, like.
Actually, basically, we have done tensile testing. So as per ASTM standard, we need to have minimum 3 mm thickness. So all the samples were made for 3 mm thickness. So we used a mold. We took 1 feet by 1 feet by 1 feet mold, and we poured that epoxy clay mixture, and then we left it for curing, and then we cut the samples using water jet cutting, and then we use the samples for testing.
Okay, that's why it was not mentioned somewhere else. So that's why I want to confirm. Apart from it, there is one more thing I want to know, that in your TM analysis,
Yes.
whether you have prepared the sample by using ultramicrotome, or whether you have dissolved in some solvent and later pour some one drop over there in
Yeah,
the
we took support from the metallurgy department of IIT Madras. So
okay.
we gave a sample. They used as I mentioned, ultra microtomy.
Ultramicrotome. Okay.
From that only they were able to, because as you mentioned, we need a very thin sample for TM. Otherwise, you can't get that images. So
Okay.
with their support, we were able to get do the testing, the TM.
Got it, sir. Got it. And final one, the part you have shown, the second part particularly, it's a polymer composite work, or the civil engineering something. The second part which is you show means that
It's
part.
not a, it is not a composite. It is not a polymer. Basically, it is the
Okay.
ultra high performance concrete. Actually,
Okay. Got
I
it.
wanted to show that image because I used Kalski bar, so which is the one
Mm-hmm.
external technique which we use it
Mm-hmm.
to achieve high strength. That's why I showed that it is a concrete. It is not polymer.
Okay. Yeah, got it.
I just wanted to show that external technique, and I wanted to show that the application of DIC in that study.
Okay. Thank you, sir. Got it. Thank you, sir.
Thank you, sir. So any other questions? Session valuable for all us, sir. Thank you so much, sir.
Thank you, Dr. Dinesh Babu, and I also I would like to thank the organizers, Dr.
Yes, sir.
Satish Kumar and others for inviting me to give me a talk in this forum. I am honored. Once again, thank you. Have a pleasant evening.
Thank you, sir. Thank you.